Okay, suppose the matrix A is given by this. Negative 1, 1, negative 2, 4, 2, 3, 1, 4, 1, 2. Now this matrix, you know, the first column, 1, negative 2, 4, this is gives us the image. So we plug in I, we get the thing. We plug in J, we get the second column. We plug in K, we get a third column. Okay. Now we are working in three-dimensional space. Maps between three-dimensional space, I, J, K. So we know where does I and J, K, the image of these three vectors, then by linear combination, we know any other vectors, okay? Where does any other vectors go under this operation? Okay, for instance, if we operate this matrix on this vector, so this is the A. Now this is the, let's see this vector X to be is 2, 2, 3. Component wise, this means 2i plus 2j plus 3k. Okay, so under this operation AX, then we get you see, then we get A operate on 2i, we operate on 2j, we operate 3k. Now A does nothing to the coefficients. So this actually we get A twice AX on I, and twice AX on J, and 3 times AX on K. Okay. Now we know the output and A, the I goes to the first column of A, which is 1, negative 2, 4. So it's 2 times the first column, 1, negative 2, 4, plus twice the second column, plus 3 times the third column of A. Okay, third column of A, which is the 4, 1, 2. Now we are dealing with linear combination of vectors. Then we use multiplication of vectors by scalar multiplication of vectors. Then we get distribute this 2 inside, so we get a 2, negative 4, 8. Distribute this 2 inside, so we get 4, 6, 2, plus 6, 3, so this is 12. And then add all the 3 components all together. So we get a X component, Y component, Z component. This we get 18. This we get 5. This we get 16. Okay, so this is using linear combination of columns. Now we can also use use dot product. So this we use what we just did. We use linear combination of columns. We can also work out by rule operation. Now rule operation says the following. So the matrix 1, 2, 4. We're dealing with rule 2, 3, 1. 4, 1, 2 with this vector. So this is A, this matrix is A, this is X, this thing is X, vector X. So we are dealing with A dot product, A times X. Now if we write the rule of A, we write down A as rules. Okay, so it has 3 rules. A as rule vector R1, rule vector R2, rule vector R3. Here, R1 is 1, 2, 4 as rule vector. R2 is 2, 3, 1 R3, the third rule for 1 and 2.
For A, isn't in row one, row one, or I'm sorry, row two, column one, isn't that supposed to be -2?
-2? Yes, you are right. Sorry. Thank you. Okay, then we work out this by rule operation. Rule operation says if you multiply, then if you multiply, what do we get? So we get, in this case, we get 3, the column vector. So it's a 1 row, so 1 column, 3 rows. Okay, so it's just 3 rows, 1 column. So it's 3y. So the ij, so it's a ij. So it's a I is column, j is row. So I ranges from 1 to 3. 1, 2, 3. J is just 1. No choice for j. Okay. So the ij part, the result, the ij part of the entry is given by I through dot product with dot product with x. J column. So here we only have 1 column in x. Okay. So we should get so I is from 1 to 3. I have 3 choice for rule operation. So we get 3 rows, 1 column. So you see R1 dot product. You see R1 dot product with x. This gives us 1, 2, 4 dot product with 2, 2, 3. Then we get, okay, then we get a 1 component-wise multiplication. 2 times 2 plus 4 times 3. Now you see the first entry, first row, first column. Then we get it. This is 2 plus 4 plus 12, which is exactly 18. You see, the result we get is, we should get 18, 5, 6. Okay, the result we should get 18, 5, 6. So we should get 18, 5, 6, 16. So you see this result, we get exactly 18. Okay, exactly 18. Now second row, first column, we get R2 dot product with this x. R2 we write R2 which is -2, 3, 1. Dot product with 2, 2, 3. Then what do we get is -2 times 2 plus 3 times 2 plus 3, which is -4 plus 6, 2 plus 3, we get a 5. You see exactly we get the second row as 5. Okay. Now the third entry. Now the third rule is, you see we have the third rule 4, 1, 2. Okay. So third rule 4, 1, 2. 4, 1, 2. Dot product with 2, 2, 3. Then what we get is 4 times 2 component-wise multiplication, and they add 1 times 2 plus 2 times 3. So this is 8 plus 2 plus 6, which is 16. You see exactly the entry is the last entry 16. Okay. So we can, when we do multiplication, okay, we can do either column picture or the row picture. Okay. Then we get exactly the same result. Okay, more examples. Two, 3, 5, 1. Now this matrix means if we so this is A, this is the X. X is 4, 2. Now this matrix, the first column tells us if we plug in I, then we get under this operation A, then we get a 2, 5. If we get J, input J, under the operation of A, then we get the second column. Then we get a 3y. Okay, then we get a 3y. Now, if we get x, if you write x as 4, you see, you can get x as 4, 0 and 0, 2. So this is the 4i plus 2j. So under the operation A, x will goes to, you know, 4 is just 4, keep fixed. A just I, you know. So let me write here. So Ex will equal to I goes to 4 times the image of I, which is 2, 5. Now the coefficient is fixed. 2 is just 2. G goes to, according to this rule, G goes to 3, 1. Okay, and then we get, this is a linear multiplication, scalar multiplication. So this is 8, 20 plus 6, 2. Add them together, component wise. 8 plus 6, we get 14. 20 plus 2, so we get 22. So this is rule picture. Sorry, this is column picture. Now by using the rule picture, now if you write a 2, 3, 5, 1 as you know, vector rule 1, vector rule 2. So you see rule 1, you compare, rule 1 is 2, 3, rule 2 is 5, 1. Now now E multiply X, then we get a 2 rule 1 column, 2 rule 1 column. Okay, so A is, you see, A is 2 by 2, 2 by 2. Now X is 2, 1. So this coincide. This coincide. Then you get delete the adjacent numbers 2 and 2. So you get actually the output is 2, 1. Okay, 2 rows, 1 column. So you see the first entry 1, 1 will be R1 dot product with X. So this will be 2, 3 dot product with, now X, we already know X is a 4, 2. Okay, X is a 4, 2. Vector X is 4, 2. So we dot product with 4, 2, 4, 2. So we should expect we get the first entry should get a 14. Remember, so our result is 14, 22. So you see, if we use dot product component wise multiplication, 2 times 4 plus 3 times 2, then we get 8 plus 6, which is a 14. 14, which is exactly 14 here. Now the second rule, dot product with X. This will be 5, 1. Dot product with 4, 2. And you see what we get is 5 times 4 plus 1 times 2. 5 times 2 is 20. 20 plus 2, 22. So you see, exactly we get a 22. Okay. Okay, more example. Now the matrix A is 1, 2, 2, 0, 4, 1. It has 3 columns. Okay, it has 3 columns. Now you see each column gives the output of certain vector. Okay, i.e. we should have a 3-dimensional space. Okay, each column gives us the image of each dimension. Now we should have X, let's X be a 3-dimensional space, 3-dimensional vector, 3, 1, 1. Okay, 3, 1, 1. So this the action of A is the following. It maps the first component I, map it to the first column. J map it to the second column, 2, 0. K map it to for y. You see the output is two-dimensional vector. Okay, it's a vector that has two components. So it's a vector in a two-dimensional vector space. Okay, although our input x lies in a three-dimensional vector space, it has three components. Okay, the output turns out to be in a two-dimensional vector space. Now x, you write x as x is 3y1. So this is 3 0 0 plus 0 y1 and 0 y 0 plus 0 0 y. So this, the first is 3i, the second one is j, the third is k. Okay, now under this operation x, under this operation e x on x, vector x, then what output should be 3 is a 3 x my the I, you see the I will goes to 1 2 according the first column. Now j get the second column. Now the coefficient of j is 1, so we get just 1 times this, the second column of a. Now k is, now the coefficient of k is 1, so it's the third column. So we add them together, so this we get now multiply. So this is 3 6 plus 2 0 plus 4 1. Now we component add them. So the first component we get a 3 2 4. Okay, 3 2 4. So we add them 3 2 4. So which is add them together. So we get a 9. Okay. Then the second component 6 0 1. So add them together. So we get a 7. Okay. Okay, we can also use the rule picture. Now you see, here A is 2 rows, 3 columns, 2 times 3. Now the x is 3 rows, 1 column. Okay, if you multiply them, so this 3 and 3, they cancel each other. The output is 2 1. Output is a vector 2 rows, 1 column. Okay, now the first row, first column will be now here you write A as 2 vector form. A as 1 2 4 2 0 1 as row vector form, which is R1 R2, 2 rows. So you get R1 by compare, which is a 1 2 4. R2 is 2 0 1. Now remember our x is 3 1 1. X is 3 1 1. Okay, so the first entry we expect we get this is our result 9 7. So the first entry is R1 dot product with x, which is 1 2 4 dot product with 3 1 1. So component wise multiplication, they add them together. So it's 1 times 3 plus 2 times 1 plus 4 times 1. So you see this is 3 plus 2 plus 4 is 5 plus 4, which is 9, which is exactly is the entry 9. Okay, the second row times this first column, we get 2 0 1, and then the x 3 1 1. So what do we get is component wise multiplication. They add them together, 0 times 1 plus 0 times 1. So we get 2 times 3, you get 6 plus 0 plus 1, which is exactly 7. You see 7 is exactly 7 here. So this works. Any questions about these examples? Example. Consider this matrix, this action, this matrix. A is 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay, let's see what this matrix A does. What this matrix A does. So we multiply the vector, let's see, the vector x. The vector x is, let's use the vector maybe v, x, y, z. Okay, now A tells us that if we plug in I, then the output is the first column, 0, 0, 1. Plug in J, which is the key here. We plug in G, then we get 0, 1, 0. The second column, which is again J. So G mapped to J, so this does not change. Does not change. So if we plug in key, what we get is 1, 0, 0, which is the first entry I. So the what we get is with the matrix A fix J, okay, does no change for J. But then switch key with I, okay. Then if we write V as x, y, z, if we write x component as xi, y component is as yj, z component is zk. Okay, remember, then the A acts on V. Then remember, it switch k with I. G is fixed. So x, y, z, their coefficients does not change. So this will be x, I goes to k. Y is yj is yj. Z is z. K goes to, remember, k goes to I. K goes to I.
Professor, I have a quick question.
Yes.
Is it because that they're the same, they can be interchangeable?
This is because what this matrix does. This matrix does. Matrix is a rule, tells you what output you get once you input a vector. Yeah, like a function. A function is you plug in a number, output number. You can choose whatever the output is. This is, you can define it. Okay.
Okay.
Yeah. So here, this matrix tells you a rule, what you input, what output you should expect.
Mm-hmm.
Yeah.
So for K, like if you were to put in 1, you would expect 1 to come out then?
So here we are input vector. We are not input the numbers. So we put the number vector ijk. Ijk, they are vectors.
Okay.
Yeah. So if you work out in this manner, so remember ijk is the first, second, third component,
Mm-hmm.
which correspond to x, y, z.
Okay.
Okay. Later, I will give you several numbers. You will see how do we work out this thing by numbers. Okay, using the rule and pick a rule or column picture. Okay. So this we will this excuse me. K is 0, 0, 1. G is 0, 1, 0. I is the first one, ijk, 1, 0, 0. Z. Now if you distribute inside x, scalar multiplication, so it's 0, 0, x. Okay, so this is the y distributed to 0, we get a 0, y distributed to 1, we get a y times 1, so we get a y times 0, we get a 0. Now z distributed inside component wise, So we get z times 1, we get a z. Z times 0, we get a 0. Z times 0, we get a 0. Okay, and then we have the vectors. And then we add component-wise. So we got a 0 plus 0 plus z, 0 plus y plus 0, x plus 0 plus 0. So you see, what do we get is z, y, x. You see what happened? What happened is we plug in a vector xyz. Plug in a vector xyz. What do we get? Output is zyx. Okay, what essentially this thing, this map, this A matrix does is it switch the first component with the third component. Okay, so this is why we see it's switch I with K. Okay, it is switch I with K. And then the second component is a fixed. Y is again Y. Okay, so it fixed the second component. Okay, it switch with X and Y, X and Z. X and Z. Okay. Let's see one easier. Let's see maybe this example. Maybe do an easier example if you're confused. Okay. Now let's switch example. Let's do a less complicated example. Now suppose on the two-dimensional space xy plane. Okay. So suppose we have a point. And suppose this is what point? Let's see, it's 3. So let's see, it's 3, 1, 3, 1. So this vector, we have vector O, this is A, OA. OA. So A is 3, 1. OA is, of course, also 3, 1. Now we have another point, A prime. A prime. A prime. Okay, A prime is 1, 3. Okay, if you switch 1, 3 with 3, 1, you see A and A prime, they are symmetric with respect to what? They are symmetric with respect to this line. The bisector of the third and the first quadrant. Okay, so this is line y equals x. If you flip the thing, you get actually A flip to A prime. A flip to A prime. Okay, so this operation flip with respect to flip a point with respect to y equals x is actually we can achieve this operation by a matrix multiplication. Okay, so you see, if this flip, what do we get if we input I? What's the, if we flip with respect to this line, y equals x, what do we get for I? For the vector I? What do we get? If we flip I, what do we get? Anyone know?
J.
If we flip I, you see, flip x-axis, we get a y-axis. We flip I, then we get a j. And then similarly, we flip j, we get I. Okay, so this operation, we flip I, we get j. And then, which is a j is 0, 1. Okay, the second component. If we flip j, then what do we get? What we get is I by symmetry, which is 0, 1. Okay, so this operation flip with respect to the line y equals x. is given by this. So correspond to this matrix multiplication. Here A is used. Here let's use the M matrix multiplication. So this correspond to, let's use P. Let's maybe use P. So you see it's I. The output of I tells you the first column, 0, 1. The output of J tells you the second column, 1, 0. Okay. So this flip X with Y. This flip X with Y. Okay. So if you do anything, so you get, so you see 0, 1, 1, 0 times XY. Okay. This will be, you use the rule picture, you can use the rule picture or the column picture. Okay. Now this, you write XY as XI plus YJ. Okay. X part. So you see it goes to I goes to X, I goes to J, J goes to I. So this will be, J is 0, 1. Y is, I is 1, 0. Now if you put this together, so this will be 0x, and this will be y 0. So add them together component wise, so you get a yx. Okay. So actually, according to what the argument, then we should get a yx. You see exactly this flip the first component with the second component. Okay. Flip xy, so we get a yx. Okay. If you use rule picture, you see, if you write this matrix P as R1, R2, here R1, you compare. So R1 is 0, 1. R2 is 1, 0. And then you dot product with R1 dot product. Let's see this vector XY. Then you get 0, 1 dot product with the XY. Now you see the first multiply the first, the second multiply the second. So 0 times X plus 1 times Y, which is exactly 0 plus Y, which is Y. Okay. So you see, this is exactly the first entry, we get a Y. Okay. Now the second rule, R2, is 0, 1, 0. Now R2 dot XY. Then we get 1, 0 dot XY. Component wise multiply, and then add. So we get 1 times X, which is X, 0 times Y, we get a 0. Which is X plus 0, which is X. You see the second component. The second component, which is exactly X. Okay, which is exactly X. Okay. Okay. Let's see another example. Matrix multiplication. Let's see this matrix. A is this matrix. 2, 1, 3, 1, 2, 3. Okay. It has 2 columns. Then what we do is this X as 1, 1. Okay. So here X lies in a 2-dimensional space. And then we have X lies in a 2-dimensional space. It has 2 components. And then for each component, okay, for each component, X has 2 components and A has 2 columns, okay? Because we know the image for each component, okay? The first component, the image is the first column. So this matrix A means the first column I equal to 0, 1. Map under the map A, it should get the first column. Okay. Now the second component, J, is 0, 1. Under the map of A, it should get the second column. 1, 2, 3. Okay. Now here X is 1, 1. X is 1, 1. X is 1, 1. You can write it as 1, 0 plus 0, 1. So it's I plus J. I plus J. Now under this map A, let A X on X, then we should get now the output of I under the map of A, we get 2, 1, 3. Now the output of J under this map A, under this rule A, we should get 1, 2, 3. Yeah. So we add component wise. 2 plus 1, we get 3. 1 plus 2, we get 3. 3 plus 3, we get a 6. Yes. Any questions? Any questions? Okay, we can also use the rule picture. Rule picture, you see, what is the first rule, second rule, third rule? The first rule of A, R1 is 2, 1. Okay. You see R1 dot product with X, which is 2, 1. Dot product is 1, 1. Then we get 2 times 1, 2 times 1, and then 1 times 1. Which is 2 plus 1, which is 3. You see, which is exactly the first component 3. Okay. Now R2, the second column of A. You see the second column of A. The second column of A is 1, 2. Okay. So this is gives the R2. This gives you the R1. This gives you the R3. R3 is 3, 3. Okay. So R2 is 1, 2. R3 is 3, 3. So then we dot product with X. It's 1, 2 dot product with 1, 1. So first component goes to first component, second component goes to second component. So this we get 1 times 1 plus 2 times 1, which is 3. You see the second component, which is exactly second component 3 here. And the third component, we should get a 6. Okay, we should get a 6. Now indeed, you see R3 dot product with X is, we already know R3 is 3, 3. Dot product with X, 1, 1. So we get 3 times the first component 1, and the second component 3. Dot product multiply the second component 1, which is 3 plus 3, which is again 6. 6, you see, which is exactly the 6 here. Okay, so multiplication, we can either use rule operation, we can also use column operation. Okay, we get the same result. Okay, more example. Find a matrix P such that P XYZ we plug in this XYZ, this vector, to P. Then output is YZX. Okay. You see what happened to this this operation P? What happened? So here, if you write in this manner, we input XYZ. Under the operation P, we output YZX. Okay. Okay. Okay, we write the following. We write the following. Okay, we write the following. So you see, we do the following. So the left side is I. If you write it in this manner, X00 plus 0Y0 plus 0. So this is X I plus Y G plus Z of K. Now the map, the output, if you write in this form, so this output will be Y times I plus Z times K plus X times Z times J, X times K, X times K. Okay, so what we see is we can pair it in this form. So X, remember when we do linear, when we do matrix multiplication, the coefficient is fixed. So you see I goes to K, you see YG maps to YI. So you see J goes to I. And then Z is fixed. K goes to J. Okay. So you see I goes to K. Yeah. This is a 001. The second component G goes to I, which is a 010. And K goes to what? K goes to J, which is a 0. Yeah, I get it wrong for I. 010. So we can write, the image of the I is the first column of the map. Okay, we write the first column. What's the first column? The first column is the output of I. The second column is the output of J. The third column is output of K. Okay, so first column, output of I, which is 001. The second column, output of J, which is 100. Third column, output of K, 010. So actually, this is the P. This is P. This is the P. So what P does to this XYZ is, you see, it permutes the letters XYZ. Okay, it permutes the letter XYZ. Because here we only have 3 numbers, 3 letters XYZ. The permutation, if we do enough times permutation, it will recover itself. Okay, it will recover itself. So you see, let's see what we did here. So what P does is XYZ under P goes to YZX. Okay, you see what essentially this does is X from the first place go to the third place. Okay, so what essentially this does is this. Okay, what it essentially does, X from the top becomes the bottom. Okay, and then we lift Y and Z by 1 unit, Okay, 1 unit. Now if we do this thing again, P, what do we get? We get the thing, we should move this, the top letter is Y. Okay, remember the top letter is Y. We move the top letter to the end, And then the remaining letter Z and X, we leave it by one step. Okay. Lift Z and X by one step. And then if we apply P again, the top entry, the top component Z, it goes to the third, the bottom entry. And then the remaining lift upward by one. You see, after three times operation, actually we recover XYZ again. If you do this thing, you can check P times P times P, which is the identity matrix. No change at all if you do P 3 times. Okay. So here P is a permutation matrix. Permute things around. P is a permutation matrix. P is a permutation matrix. Permutation. Okay, permutation actually turns out to be an important topic in group theory when we study symmetries between objects. Actually, the some history of the algebra. Okay, people know how to solve quadratic equations using quadratic formula, and then after people solve degree 2 case, and then people trying to solve degree 3 and degree 4 case, and then finally people find a formula by radicals, how to solve degree 3 and degree 4 using radicals, although it can be complicated, but finally people have a formula. And then people trying to study degree 5, degree 5 equations. And then it turns out a genius mathematician, Galois, he used permutation theory, permutation groups, actually showed that degree 5, we can usually, we cannot solve it by radicals, okay? The solution exists, but we cannot solve it using radicals, okay? So this turns out to be really important discovery in mathematics. It motivated something called Galois theory. You see, using linear algebra, using matrix, we can actually do permutations. Okay, do permutations. So this linear algebra has a lot of application in Galois theory, study symmetries of objects. Okay, let's see more examples. Example. Find a 2 by 2 matrix. Okay, find E, find a matrix E. So find a matrix E. 2 by 2 matrix. Such that so that subtracts the first component from the second component. Second component. Ooh. From the second component. Okay, so it means this E. Okay, suppose we X on a vector, two-dimensional vector. Then the output is x. The first component keep fixed, and then we subtract the first from the second. Okay, so we want such a e. Okay, such a e. Okay, so if you write this thing as, what we do is we separate x and y. Okay, separate x and y. So you see here, this is x negative x plus 0 and y. Okay, so you get an x, factor out x, is you get a y negative 1. Then you get a y 0 1. Okay, remember, so this is the e xi plus yj. Remember, x, y, they are numbers. They are fixed. Okay, so this tells us, so this is x, e on I, and e on j, y times e on j. Okay, so you see, x corresponds to x, y corresponds to y. So this correspondence tells us that this e x on x, e x on I should correspond to this vector. And e, the output of e, if we input j, then we should get the second one, the vector 0 1. Okay, so we can conclude that e is this operation. We plug in I under e, then we get ei, which is 1 negative 1. So the output of I, the output under e of I, if we plug in I, is 1 negative 1. So this gives us the first column of e. So the first column of e should be 1 negative 1. Okay, now we plug in g under e, we get eg, which is 0 1. This tells us the second column is 0 1.
So that is the matrix field. Let's check with the rule operations. We check with the rule operations. Let's check with the rule operations.
So what we get is the first row times the first column. The first row times the column x1. So we get 1 times x plus 0 times y. Now the second entry, so we get the second row times the column. So it's negative 1 times x plus 1 times y. Okay, so this is exactly, if you work it out, this will be x, y minus x. Okay, then we're done for the problem. More examples. Now we want a matrix E such that 3 by 3 matrix. We want example. Find E such that okay, what happened is if x goes to x, x is fixed, okay, z is fixed, and y, but y, the second component changed. Okay, we write in this form, we put x together, we put y together, we put z together. So we write the right side as, you see, how do we split x? The terms that has x, and then the terms has y, and then the terms has z. Okay, Then you distribute. So this is x, y, -1, 0. And y you get 0, 1, 0. And z you get 0, 1, 0. Okay. So the left side is e xi plus yj plus zk. Now this operation is linear, so we can distribute the coefficients. Distribute. Okay, so you get xei plus yeg plus zek. Okay, I see this x correspond to this x here. So we get this e dot I should goes to this e. So we get compare ei should be 1, -1, 0. Okay, if we compare, let me use different color. If we compare this one, then you get the coefficients of y. Okay, now if you get they correspond to each other. Now if you choose a different, let me choose a different color. Let's use now the compare z, the terms that has z, this has z, and they correspond to each other. Okay, so we get so we get ej should be 0, 1, 0. Okay, this is the second column of E. EK as 0, 0, 1. So this is third column of K, third column of E. So we can write E as matrix E as the first column. First column is output of the I, 1, -1, 0. Second column is EG. So we get a 0, 1, 0. Third column, we get a 0, 0, 1. Okay, then we're done. Okay, more examples. Okay, find a 3 by 3 matrix E. So this question, what 3 by 3 matrix? If we multiply this E, multiply XYZ. Here T means transpose. Here I don't want to write column vectors because it takes more space. So I just write rule vectors, then we switch it, transpose it. So we transpose rule into columns, transform rules into columns. So to give x, y, z plus x. Let's see, this is T. So I should write it vertically. I use the letter T to transpose. So horizontal will becomes vertical even transpose. Okay, let's see. Now this says E. We want a matrix E such that we multiply x, y, z. So we want to get this x, y, z plus x. Okay, we can write it in this form: split x, y, z. X 0, x here, And then the remaining things, so here we have 0, y, 0, and then we have 0, 0, z. Okay. So and then factor out the x, y, z. This is x, y, 0, 1. And then factor out y, similarly, y, 0, 1, 0. And z, 0, 0, 1. Okay, the left side, you write it as e times xi, yj, zk. Now remember, you can distribute. This thing operation is linear. So you can distribute. You factor out x, y, z. So this you get xei plus yeg plus zek. Then you compare. You compare coefficients. The terms that has x, and then the terms has y. You see the terms that has x. Terms has x. They coincide. Then the terms has okay, let's use another color. The terms has y. Correspond to the term has y. Okay, the term is z. Then the term is z. Okay, so finally we see e. If we plug in I under this map, e output is ei, then what we get is ei is 1, 1, 0. So this is the first column of e. G under e goes to eg. Eg is 0, 1, 0. This is the second column of e. Now k goes to ek, which we get 0, 0, 1. So this is the third column of e. Third column of e. So we finally put all three columns together. Three columns together. So y, 0, 1, the first column. The second column, 0, 1, 0. Then we get a 0, 0, 1. Then we are done. We are done. I think we forget something. Yeah, it's right. It's right. Okay. Okay, what this E does is we add the first component X to the third component Z. Okay, then X, Y, Z, X, and then the first component X, Y, they are fixed. Excuse me. Now this is actually invertible. This is invertible. So here we add the first component to the third. We can also subtract the first component to the, we can also subtract the first component to the third. Okay, then is that this is totally invertible, totally invertible. So if now what E inverse does is X, Y, Z. So here last time what E did is we add X to the third component Z. Now E inverse, so the inverse of addition should be subtraction. Okay, so we should the first two keep it fixed, and then the third subtraction, subtract X. Okay, subtract X. Now if you work out as what we just did, you will see actually E inverse is okay. So again, we still have this 1, 1, 1, but here this we got a 0, -1 here, 0, 0, 0, 0. Okay, the only change is, let me, the only difference is here we have -1 and here we have 1. Okay. Okay. So this is what E inverse does. And then you can check. What you can check is, if we do the inverse, if we do E and then do the inverse, then nothing changes. Okay. We subtract and then we add, nothing changes. Okay. So what you can check is E times E inverse. The composition is, you see, if you do the composition, X, Y, Z, then the first step, what you get is X, Y, Z subtract. And then remember E, just add the first entry to the third. So you get X, Y, Z minus X plus X. So you get a X, Y, Z. So you plug in X, Y, Z, output is again X, Y, Z. Nothing changes. Okay, everything is fixed. So in this case, E and E inverse, of course, this is identity matrix. Identity matrix. I. And then it's dimension 3, so it's a I3. So if you write down this, you get a 1, 1, 1 here, 0, 0, 0, 0, 0, 0. So this is the identity matrix. Identity matrix has 1 in the diagonal and 0 for other entries. Okay, it has 1 on the diagonal. All other entries are zeros. Okay, so this is identity matrix. You can also check use the matrix multiplication rule that we did. Okay. Okay, let's see this map, another example. Now XY projection, we project it to be X0. Okay, why is called projection? Okay, if you do the XY plane, you work on the XY plane. Suppose we have vector, this is XI plus YJ. Okay, so here this point is Y, this point is X. Sorry. This is X-axis, this is Y-axis. Now you see the output, this vector, the output, let's use the colored, the output X, so output is XI, okay? XI is exactly the thing, this direction. So it projects the vector onto the X-axis, okay? So projection, so this is why we call it a projection, okay, projection. Okay. Projection. So what matrix does the projection? What matrix does the projection? So you see, we want P, X, Y. So what we want is P, X, Y. Simply get X0. Okay, so you can write as X, you can write X, 1, 0. Okay, now you see we don't have any Y. We don't have any Y. What do we do? Well, we just let Y minus multiply by 0. No Y. Okay, no Y. Okay, so the Y part just die because there's no Y. Okay, so if you write as PXI plus YJ, so you get an X distributed, you get a PI, PJ, YPJ. So you see, this equal to X 0, 1 plus Y times 0, 0. Okay.
Now what you can see here,
By compare these coefficients. By comparing these coefficients, you see X P dot I, then we get the thing. And then what do you get for P times J? Okay, P times J goes to zero vector. Goes to zero vector. Now it's easy to understand. Now if you have a G vector G, you project onto the x-axis. There's no projection. Okay, the projection is zero because it's perpendicular. Okay, so let's see a picture. Okay, if you have x, if you have a G vector, a vector G, you project this G onto the x-axis. So you just squeeze to a zero. Okay, project onto the x-axis. You project the thing onto the x-axis. You project to a point. Okay, so J goes to zero vector. Okay, so this you can write as Pi is 0, 1, which is I keep fixed. Pg goes to 0. Goes to 0. Okay, J just is killed under this projection. So the image of I gives you the first column. The image of J gives you the second column. Okay, so this is actually P. This is the P. Let's use P1 because it projects onto the x-axis. This is P1. Now similarly, we can work out for P2, the projection on y-axis. Okay, can anyone gives me can anyone tell me what P2 should look like? Remember, the first one corresponds to x. The second corresponds to y. By symmetry. Can anyone tell me what a P2 should look like? P2 xy is 0y. Well, we don't have x anymore, so we get x 0, 0, and then we get a y 0, 1. Okay, so you see this x. So if you get this part, x P2 xi plus yj. This will be equal to x P2i plus y P2j. If you compare the term has x, you get the thing. You compare the terms that has y. Okay, so you get I goes to 0 vector, which is 0, 0. J goes to J, which is 0, 1. So the image of I gives you the first column. The image of J gives you second column. So P2 should be 0, 0, first column. The second column 0, 1. Okay. Okay. Now, what is P1 plus P2? P1 plus P2 is this 1, 0, 0, 0 plus 0, 0, 0, 1, which is the identity matrix. Identity matrix. Identity matrix, identity map, or identity matrix. Now here it's degree 2. Okay, so this is called completeness relation. This is called completeness relation. You add all the projections together, you should get the identity. The idea is the following. So if you have a vector xy, now you can project onto the x-axis. For instance, you project onto the x-axis. You project onto the x-axis. So this is a projection on the x-axis. And then you can also project onto the y-axis. Let's see the project onto the y-axis. project onto the y-axis. So this is actually what you get it, to project onto the y-axis. Okay, now, so if you add this together, projection on x and then projection on y, this you get the original vector itself. Okay, you get the original x itself. Okay, now if you have all possible projections, if you have higher dimension x, y, z, then you need a projection on x, projection on y, projection on z. The three projections add together, you get the original vector itself. Okay, you get the original vector itself. So once once one projection is missing, you have something lost. Okay, the vector has something lost. It cannot recover itself, not complete. Now, if you have 3 dimension x, y, z, you add 3 projections: x projection, y projection, z projection. Then the 3 projections makes the complete, okay, vector itself. Okay, recover the original vector itself. So this is called a completeness relation. Okay, this is called completeness relation. So P1 plus P2 equals to I2. This is called completeness relation. Add all projections together, then this complete the original vector. You recover the original vector. Okay. Now homework for this section 2.1. Homework. This is for problem set 2.1. So let's do number 1, number 2, number 9, part B, number 10, 11, 12, number 21.
Is this
Number
homework
33.
also due? Is this homework also due Monday, or is it?
No. I will give you 1 week.
Okay.
Yeah.
And that'll be
Usually
posted
when
in
I
Canvas?
post the homework problem, I will give you 1 week to work
Okay.
it out. Yeah.
Okay. Thank you.
Mm-hmm. Okay, now let's start another topic. Idea of elimination. Elimination. Now we solve this linear systems by picture, by column picture. We can also solve by algebra. So the idea of elimination. So suppose we have a linear system we want to solve. Okay, see this example. We already see several examples like this, but we does not do it in that manner yet. Okay, so suppose we have this example. X plus y to be 5. Now 2x plus 3y is 14. This equation 1, equation 2. Now this is on the xy plane. This is 2 lines, okay, 2 straight lines that are not parallel. So they naturally intersect at one point, unique point. Okay. Then the column pictures, if we do the column picture, then this says certain vectors, the 2 column vectors are linearly independent. They span any vector on the xy plane. In particular, they span for the coefficients 5, 14. Okay, this vector. Then we have some linear combination xy that gives us the result. Okay, this is the column picture. Now we can also solve it by algebra by reducing the number of variables. Okay, so here this 2 variable function, 2 variable equation. Then we reduce 1 variable by algebra. So here we multiply equation 1, multiply equation 1 by 2 by negative 2, then add it to add to equation 2. Okay, multiply equation 1, then we get by negative, so we get negative 2x, negative 2y equal to negative 10. Now add to equation 2, then we get a 2x plus negative 2x, then we get a no x anymore. 3y plus negative 2y, then we get a y. So we get a y equal to 14 minus 10. So we get a y equal to 4. Okay. Okay, the first equation is again the first equation. So it's x plus y to be 5, and then y equal to 4. Okay. Now we can substitute y by 4. So we get x plus is 5 minus y, which is 5 minus 4. Substitute it back, and then y equal to 4. Okay, y equal to 4. So we get the equation. So we get a solution. X is 1, y is 4. Okay, so this technique, this is very easy. We know how to do this in high school. It's called elimination. We try to reduce the number of variables by, manipulate this coefficients by multiply certain numbers and then add them together. So we cancel certain variable, then we reduce the number of variable. Okay, so here the letter xy is not important. The letter xy, you can use any letter, AB or something. So this actually, what is important is the coefficients, the numbers. Okay, so if you write it, you can simply manipulate the coefficients in this manner. So if you write the coefficients in this, if you read the coefficients, it will be y1, x plus y, the coefficient is xy. And then the coefficients for the second rule, second equation is 2, 3. Okay, 2, 3. Okay, 2, 3. Now we have another thing for the right side numbers, 5, 15. So we write here 5, 15. Okay, so we don't need the name of the variable. Okay, because you can also solve it in another variable. Just change the name of the variable. It does not change the problem. Just change the name. Okay, now this is called augmented matrix. Here we added another column, not just the coefficients matrix. We add another column which comes from the right side, the number of the right side. Okay. Okay. Now, how we manipulate these coefficients to elimination? What we do is we do rule operations. Okay. So multiply, you see, multiply equation 1, then add it to equation 2. So this actually, we do operations, rule operations. We only allowed to do rule operations. We do rule operations. No column operations. Okay, this matrix, augmented matrix. Matrix. Okay, for instance, this one is augmented matrix. So what we do is, let's do this operation. So remember, the first rule in the augmented matrix corresponds to the first equation. So we multiply the first equation by -2. So we multiply the first rule by -2, and then add it to the rule, second rule. So this actually will replace R2. Okay, so replace the second rule by R2 plus the first rule multiplied by -2. Okay, so you see what do we get? The first rule keep fixed, y. Okay, the second rule we should add -2 times the first rule. Okay, so we get 0, 1. And this side similarly, this is the 5 keep fixed. This we should the 14 should plus -2 multiples of the 5. So this would be 14 minus 10. So this is the 4. Okay. And then what we get is, so this correspond to, remember, this correspond to x plus y is 5. 0x plus y is 4. Okay, if you read the augmented matrix for this. Okay. And then we do root operation again. Now we add the first rule. So we -2 R2 plus R1. Replace R1. So we add -1 multiple of the second rule to the first. Okay, so we get 0. This is 0. So the second keep fixed. So it's this is 1. Now next one we get a 0. Okay, y minus 1. And then this we get a 5 minus 4. So if you write it more carefully, so this will be y minus 0. Oh, sorry, 1 minus 1. 5 minus 4, which is equal to 1, 0, 1, 0, 1, 4. So this correspond to we have x, we have no y, 0 y. We said x is 1, and this correspond to y. There's no x anymore. We only have y multiple of y. Okay, so this is actually the idea how to do how to do elimination. Okay, we do rule operations such that we finally the right side. This side is identity matrix. The last step is identity matrix. So what a rule operation is valid, is allowed. So for rule operations, the 3 types of rule operations are allowed. We do rule operations. This is exactly comes from the manipulation of the equations. Okay, add certain equations, certain multiple of equation to another equation. Okay, now you are not allowed to do column operations. Okay, 3 types of operations. 3 types of elementary linear equation, elementary rule operations. Okay, what first one, we can switch the 2 positions of 2 rules. We can switch 2 rules. Now this corresponds to we switch the location of this equation. Okay, if we switch these 2 equations, this does not change our solution. Okay, does not change the solution. So we can switch the equations, switch the position of 2 rules, and then we can multiply a non-zero constant or a non-zero scalar. Multiply a rule by a non-zero scalar. Okay, and then 3 we can add, like what we did for equations. We can add a multiple of, for instance, for equation 2, we add some multiple of equation 1 to equation 2. So this corresponds to, we add a rule, a certain multiple of a rule to another color, to another rule. So add to a rule a scalar multiple of another rule. Okay. Okay, some remark, maybe note, remark. Let's call it a remark. Okay, all the above 3 types of operations are invertible, so that we can go back and forth. So we do not introduce something new, we don't lost any information. So this is equivalent transform. All the above 3 types, all the above operations, rule operations, are invertible. For instance, equation 1, the operation 1, swipe the 2 rules, and then we can do it again so that it recovers the original position. Okay, so it's invertible. Now multiply a non-zero scalar, then we can multiply its inverse. Okay, the inverse of this scalar. For instance, if we multiply 5, and then we multiply it by 1/5, so we recover the original thing. And then 3, we add a rule to a scalar multiple of another. So we can also subtract that thing, so that we recover it again. Okay, so this is invertible. So so this is equivalent transform. So we don't introduce new information, or we lost some information. We don't lost any information. Okay. Let's do some examples. Quickly do some examples. Okay, example. Let's see this example. 2x plus 4y minus 2z is 2. 4x plus 9y minus 3z is 8. Negative 2x minus 3y plus 7z is 10. Now, if you write down the, let's see what happens. Write the augmented matrix. So read the coefficients. So this is the first rule. X coefficient is 2, y coefficient is 4, z coefficient is negative 2. And then we have this 2, 8, 10. Now the second rule, x coefficient is 4, y coefficient is 9, z coefficient is negative 3. Third rule, x coefficient negative 2, y coefficient negative 3, z coefficient 7. So we have augmented matrix. And then what we do is this side. Okay, we clear x variable. How do we clear x variable? Well, we can multiply equation 1 by negative 2 and then add to equation 2. Okay. So equation 1 multiplied by 2, add to equation 2, and then replace equation 2. Okay, so this will be the first, and also we equation 1 plus equation 3. Replace equation 3. Okay, so this actually the rule operation says the first rule R1 R1 multiplied by 2 plus the rule R2, and then we replace the R2. And then R1 plus R3 replaces the rule R3. So if you do that thing, you get 2x plus 4y. The first keep fixed. Minus 2z is 2. And then you have y. Now x is eliminated. Plus z is 4. And then for equation 3, equation 1 plus equation 3, add, x is 0 here. Now the y coefficient is 4 plus negative 3. So get a y here. Now the z, we get a negative 2 and a 7. Add them together, you get a 5, which is 12. Now the corresponding augmented matrix will be 2, 4, negative 2. And then here you have 2. Now x, you get a 0, 0. Y, you get a 1, 1. Z, you get a 1, you get a 5. And then 4, 12. Okay. Now elimination, do elimination again. Eliminate the y. Eliminate the y. Okay. Eliminate the y. So what do we do is, let's use 4, 5, 6. Now what we do is, 4 keep fixed, and then 5, negative 5 plus 6, replace equation 6. So we get 2x plus 4y minus 2z is 2, y plus z is 4, and then 4z, y is eliminated, which is 8. Now the corresponding rule operation is negative R2 plus R3, replace R3. So the augmented matrix, we get is the thing. The first keep fixed, second keep fixed. This we get 0, 0. We get 4, we get 8. Okay. Then we divide. So equation we get divided by the last 4z equal to 8. We divide 4. So we get z is 4, z is 2, y plus z is 4, 2x. This equation we can also clear the factor 2. Okay. 2x plus 4y minus 2z is 2. We can divide by 2. So we get x minus 2 plus 2y minus z is 1. So the corresponding rule operation is R1 divided by 2. So 1/2 R2, R1, replace R1. Okay. Now also a quarter R3, replace R3. Now R2 is fixed. So finally we get this will be 1, 2, negative 1. And then this will be divided by 1. This we get a 0, 1, 1, 4. This we get a 0, 0, 4 divided by 4. So we get a 1. 8 divided by 4, so we get a 2. Then we use substitution. You see here, the last z equal to 2. This is a solution. And then we already know z. And then we substitute here, substitute backwards. We can solve y. And then we solve yz. We can substitute to the first equation. And then we solve for x. Okay. Then we apply substitution. Or you do it in this thing. So this is the R1, R2, R3. Okay. So what you do is negative R3 plus R2, replace R2. And then negative R3 plus R1, replace R1. So what you get is, in this case, you get x plus 2y equal to 3. 3. This you get y equal to 2, z equal to 2. Okay, now this you get 1, 2, 0, 3, 1, 0, 1. This is 0, 0, 0. This is 2, 2. Okay, now the last step, you solve x. You solve x. You solve x. Now what you do is R1, R2, R3. You let R twice R2 plus R1, replace R1. So you get x equal to twice negative that thing, negative 2 times 2, negative 4 plus 3, which is 1. X equal to 1, y equal to 2, z equal to 2. Okay, so this you get under this operation. So this you get 1, 0, 0, 1, 0, 0. So this becomes identity matrix now. Now this you get negative 2 times R2. So you get a 3. So here it should be sorry, it should be negative 1 here. Negative 1. This should be 2. This is 2. Okay. So finally you get a solution. XYZ is negative 1, 2, 2. Okay, correspond to each other. Correspond to each other. So if you now here you try to write different space. Okay. Okay, so this is actually how elimination works. How elimination works. Okay. Now, actually, next time we don't have enough time. Next time we will continue to do examples of elimination. Okay, elimination. Another thing that you need to keep in mind is, so you can write it as a vector linear system. You can write this linear system as AX times B. Times B. Okay. Now, if you have an inverse matrix, A inverse times A equals to A inverse B. Okay, so you get the X is actually A inverse B. The elimination process actually gives us an algorithm how to produce A inverse. How to produce A inverse. Next time we will talk about how we actually produce an inverse of a matrix using this algorithm, using elimination, using augmented matrix. Okay, augmented matrix. Let me stop here for today. Next time we will do find the inverse of matrix by augmented matrix. Okay.